All right, today we are going to be covering how to read a chemical formula. Some of the stuff we're going to be talking about today is review. That's the way it should be. So hopefully this should feel pretty reasonable as we're going into it. First off, a little bit of vocab review. We have atoms, which are the particles of an element. We know that we have 118 elements, right? 118 different types of element. They're written on the periodic table. Those are different types of atom. The smallest piece of any one of those that is still that thing, that's an atom, right? So the smallest piece of hydrogen that's still hydrogen is a hydrogen atom. The smallest piece of gold that's still gold is a gold atom. On the other side of things, we have chemicals and molecules. Chemicals are made up of multiple elements bonded together. And the smallest particle of a chemical that is still that chemical we call a molecule. So for example, water is a chemical. It's made out of two hydrogen atoms bonded onto an oxygen atom. And one particle of that is a water molecule. All the water molecules in existence are going to be really similar to one another. In today's lesson, we're going to both be talking about atoms and we'll be talking about molecules. So remembering that difference between them is very important. On our very first day of chemistry, we talked about pure substances versus mixtures. And we learned that pure substances are things that have a chemical formula. If I have a glass of pure water, and I pull out any particle from that pure water, it's going to be a water molecule.
Wait, what is this called?
This slideshow is called, I believe, Understanding Chemical Formulas.
Okay.
It should be near the end of week 2 on the website.
Thank you.
Now, a mixture is a little bit different. If I have a mixture and I pull out a single particle, you don't know for sure what kind of molecule you'll have pulled out. For example, if I have a glass of orange juice and I were to pull out one molecule, maybe that would be a water molecule, maybe it would be a sugar molecule, maybe it would be citric acid. There's a lot of different chemicals that make up the mixture that is orange juice. And remember, everything you have ever touched or tasted or felt has been a chemical. It's all either chemicals or the building blocks of chemicals. Or a mixture of many chemicals. So water, an example of a pure substance. Orange juice, an example of a mixture. Any pure substance has a chemical formula that we can use to describe it. And that chemical formula tells us what elements are in it, how many atoms of each element are present. It may also tell us things like the charge if it's an ionic compound. And then we can go a little bit deeper once we start talking about chemical reactions. We might need to talk about like how many molecules do we have. So here are some examples of chemical formulas. H2O, right? That's the first chemical formula you probably have ever heard. That's water. It's made out of 2 hydrogens and 1 oxygen. NaCl, right? 1 sodium atom, 1 chlorine atom. C6H8O7. That's the chemical formula for citric acid. And if you would like a tiny little preview of where this unit is going, this is a Lewis structure.
What is what?
It's a Lewis structure.
Oh, I understand it.
It's just that I've used it to connect a bunch of different atoms together to show how they connect with one another to form a big old molecule. Tomorrow we'll start learning about ionic compounds. Ionic compounds are going to tend to be much simpler. They'll have, one kind of cation, one kind of anion, some number of each of those. They snap together like little magnets. After the break, we'll start learning about covalent bonding, and covalent bonding can make huge molecules like this.
This should be so fun.
It's going to be great. I actually think you will enjoy it. All right. Yes, Olivia. Yes, you may. First thing about reading a chemical formula is we have our elemental symbols. Every time we reach a capital letter, that means we're talking about a new element. That's why I've been so picky about capitalization. If I have something like a capital C and then a lowercase o, that's cobalt. It's all one element. If I have a capital C and then a capital O, that's carbon monoxide, a colorless, odorless, deadly gas, and a very bad thing. the capital O lets me know that we're talking about a new element here. So the capitalization really matters here. First letter always capital. If there's two letters, the second letter will always be lowercase. Yesterday, and again, we're still in review. Everything we've covered so far has been review. Yesterday we learned about ions, how certain atoms will gain electrons in order to fill or empty out their valence shell and thereby become more stable. And if you gain electrons, that makes you more negative, because we've added a negative. And if we lose electrons, that makes you more positive, because we've subtracted a negative. What's that? Yes. In the same way that you can lose aura, right? By doing something cringe. A cringe action is like an electron. And if you gain cringe, you lose aura. Make sense? I want you to know, Edward, but thanks to you, there's going to be a recording on YouTube of me saying that. All right. So we covered charges. We learned some things like, hey, if you have something with a charge of +1, what do you write?
Plus.
Yeah, just a plus. What if you've got something that's just -1?
Minus.
If I don't bother writing a number in chemistry, we just assume that's +1 or -1. We don't bother writing ones mostly in chemistry.
When do you do bother?
Because chemists are lazy, absolutely. Yes.
When do you do bother writing?
If it's like part of a mass, like the mass of a hydrogen is still 1 AMU. All right. If I want to talk about how many atoms are in a molecule, we use what's called a subscript. Sub means below, script means writing. So this is just like writing below an element symbol. So our charges were superscripts up above, and the number of atoms in one molecule is our subscript. So here, CH4, that 4 is a subscript that tells us how many hydrogens there are in a single molecule of methane. So this is methane gas. This is the gas that makes farts stinky. Also a very large contributor to global warming.
So our farts have.
No, it's cows. It's cows.
Your farts have methane in them. Other sources of methane, cow farts, of course, big source of methane. If you have a gas-powered stove, methane is a big part of what's in natural gas. So natural gas is mostly methane, but it has a lot of impurities in there, which is part of why it's so bad for you to be burning natural gas inside the home. It literally gives you asthma.
Great.
Yeah.
Wait, smelling farts gives you asthma?
No, actually, smelling farts does not give you asthma, because it's not the methane that's dangerous. It's the additional compounds that are created when you burn it. Specifically things like nitrous oxide, really bad for your lungs. All right, so in this chemical formula, we have 4 hydrogens. Raise your hand if you can tell me how many carbons do we have? Daphne.
1, there's no subscript.
Yeah, there's no subscripts. We assume that there is 1 carbon. Yes.
This is a question. I noticed that carbon has 4 valence electrons and it's bonding with 4 hydrogen atoms, and each hydrogen atom has 1 valence electron. Is the amount of valence electrons how many things something can bond with?
No, it
Almost.
goes up to 8, right?
It's the number of so what you're talking about now are rules for covalent bonding, which we have not gotten to yet. But if you want to preview this, you are correct. You have picked up on something true. In order to be stable, 2 things have to be true about a molecule. 1, every element that's part of that molecule has to have a full outermost shell of valence electrons. That's the first thing that has to be true. And 2, it has to be neutral as a whole. So for an ionic compound, we accomplish this by having individual atoms either gain or lose electrons until they're full, and then they snap together with oppositely charged ions to make themselves neutral. What's happening here, this is an example of a covalent bond, which again we have not gotten to yet. The carbon and the hydrogens share valence electrons. You know how if you were to draw a Lewis structure of carbon, it would have 1, 2, 3, 4 unpaired electrons? Each of those unpaired electrons can form a bond. And what hydrogen would have one unpaired electron. So basically, an electron from the hydrogen and an electron from the carbon would partner up and form a bond. And in fact, if we go back to that picture of this, you'll see there's lots of spots where a carbon has one hydrogen sticking off of it. And that line represents a pair of shared electrons. And if you don't get this, that's okay. This is future stuff that Forrest just like saw some glimpse of and was like, wait a minute, I count up valence electrons there, that adds up to 8. And yes, adding up to 8 is part of what's going on and part of what makes
So
sense.
then a nitrogen can only bond with 3 hydrogens because it has a pair of electrons already?
Yes, exactly. And indeed, there is a chemical called ammonia, which is NH3.
I had a question.
Yes.
I forgot my spell.
All right. If you remember it, raise your hand and we'll get to it. All right. So this is an example of. Oh, yes, Daphne.
So for sodium chloride, it's basically sodium giving up its valence electron to chloride, and then it bonds.
It's oftentimes described that way. It isn't really the case that like the chlorine is stealing directly from the sodium. It's more like the sodium has given up electrons. The chlorine has gained electrons, not necessarily from each other. Could be from somewhere else. And then each of them is a tiny magnet, and those magnets snap together. However, it is oftentimes described that way, where people talk about like, oh, it's like the chlorine stole the electron from the sodium. But chlorine's electron might not literally have come from the sodium. It could come from it, you know. All right. So here we have an example of methane. Now, if I wanted to give you a model of methane, it might look like this. This is one way of representing methane. Look at this formula. Look at this. Raise your hand if you have a guess for what the black sphere represents. Let's go to Matthew.
The nucleus?
It's not the nucleus. It's a great guess. It is the center of this. This is representing a molecule as opposed to an atom. No. Toby.
Is it carbon atom?
It's a carbon atom. All right, so if the black one is a carbon atom, what do we think these white ones are? Lucia?
Hydrogen atoms.
The white ones are indeed hydrogen atoms. So this represents a molecule of methane. Okay? Now, what if I had not one molecule of methane? Maybe I'm doing a chemical reaction. I want to make sure I've got the right amount of stuff. Maybe I have, as part of the chemical reaction, 3 different molecules of methane. Looking at this, how many carbons are there total? 3 carbons total. Looking at this, how many hydrogens are there total?
12.
12, because it's 4 per carbon.
How many fingers?
I'm doing
12, yeah, my
sign
fingers are a
language
little
10 and then 2.
Okay. So let me tell you how I would write that down. How I would show you, written down, that I'm talking about 3 molecules of methane.
Coefficient.
That's what the coefficient is for, yes. So the way I would do that is I would just say, there's 3 molecules of CH4. Right? And that would show me. And that means in total I have 3 carbons and 12 hydrogens. So that is called the coefficient. And the coefficient. No, that's fine. It's a lot like in math, when you can have like a coefficient in front of like something in parentheses.
Yeah.
And if you do that, it applies to everything inside the parentheses.
Yes.
Right?
You can use the distributive property.
It's called distributive property.
Yes, it is called the distributive property. Have you all done distributive property in math already?
No, we
But,
haven't.
No, we haven't.
Some of us.
kind of. We've done like the
So wait.
kind of in a different scenario.
Okay.
But like, yeah.
Okay. So
Hey,
distributive property is no
kind
more
of
than 7
how.
That's alright.
I mean, it's kind of how we just like learned
Okay.
multiplication, honestly. Like 3
yeah.
times 16, 3 times 10, 3 times 10.
Alright. So the coefficient tells us how many molecules we've got. So this would represent 3 molecules of water, and every 1 molecule of water is 2 hydrogens and 1 oxygen. So in total, that would be 6 hydrogen atoms and 3 oxygen atoms.
Wait, so Hannah, that's the important part.
This right, like if I was trying to do like the notes for this in like one tiny succinct thing, this is what I would write right here.
Because he is.
All right. So to review, we have the following things that you need to understand. We've got superscripts. Those show us the charge. We have subscripts. Those show us how many atoms are in one molecule. Here, I'll make a number of atoms in one molecule. And then we have the coefficient, which is the number of molecules.
What does sodium oxide make?
This is a molecule.
That.
That's
So
Oh, so if there were three of those, then it would be that. Oh, okay.
this is
One
a molecule.
And then,
This is an atom.
yeah. So
They
if
come
that-
off?
Yes.
three
These are
of-
great. We're going to play with
do.
these later on.
Do we get
I
Sorry,
to
say that
pick
again.
another?
So if the three means there's three, like copies of it. Like,
Yes,
that's-
exactly. So we've
Can I-
got number of molecules, how many atoms in a single molecule, and the charge up there. One thing I do want to point out. Oxide, as an anion, has a charge of -2. Lithium, as a cation, which is positive, has a charge, yes, has a charge of +1. So, think about a balance of charges. We want to end up with a neutral molecule. The oxygen moved us 2 clicks negative. A single lithium would only get me, 1 click towards neutral. But there were 2 negatives in total. So how many positive charges do I need? I need to have 2 positive charges to balance out the oxygen. That's why there's 2 lithiums in this molecule. So lithium oxide has a correct chemical formula, and it's Li2O, because this is the formula that makes this be a neutral chemical. Forrest?
Are they always neutral, or are there times when they're not?
A stable chemical compound is always going to be neutral. So when we have a stable chemical, the 2 things are going to be true about it. It's going to be neutral, and every atom is going to have a full outermost shell of valence electrons. Now with that said, sometimes we have these things called polyatomic anions,
No.
which is a negatively charged ion that is made up of multiple atoms stuck together. And those will tend to stay together, but that's honestly more like high school level chemistry.
We
You
should
can
learn
dabble
about
your
those.
toes in it in my class if you want to do some of the extension questions, but you won't be required to. Yes.
What is sodium oxide?
So sodium oxide would be like if you were to leave sodium out in air, it would probably rust. So this is rusted sodium.
So any chemical with oxygen is just that chemical rust.
Most metals, when they combine with oxygen, that's the rust that's like rusted that metal. All right, you have a class kick to finish to solidify these skills. So go ahead and head to that class kick, and you can stop this.